So I'm Pranav here with Theo and Ashish, and we're Digi, a revolutionary way to take notes. First, I'm going to start off with a little how and why we created Digi. Our team was in a Huntsman GSR way back in September using the whiteboard wall to jot down some ideas while we were brainstorming for our senior design project. We were about to call it a day, and we realized we wanted to save our scribbles for future reference. It then struck us that we had each been in similar situations many times before. Wouldn't it be nice if our notes were automatically recorded as we wrote so that we didn't have to resort by having a scribe or taking pictures? My mind instantly thought back to a stats class where I spent more time taking pictures and frantically copying down what the professor wrote instead of actually processing the information from class. This is actually one of the many pictures I took from that class because I was unable to see what was written on the board since I was sitting in the back corner and I couldn't keep up with the professor's pace. After asking friends and peers, we realized this was a problem many others forced without an effective existing solution. While video cameras record an entire lecture in video format, we wanted something that could give users a quick PDF of everything that was written. We then thought about potential constraints. Our solution had to be easy and safe to use and couldn't interfere with the natural motions of writing. So we set our sights on creating a relatively cheap clip-on device that worked with existing whiteboards and markers and digitize notes in real time with centimeter level tracking position. Next, we'll talk about some of the design ideas that we decided amongst.
So for the design ideas, we were primarily concerned with different design options for absolute position tracking. We wanted a centimeter level precision for tracking where on the board is the writing vessel. We already had a cheap $10 optical sensor solution for getting relative movement, which captured finer strokes of when the user is writing. For absolute positioning, we had three options. Firstly, we could use Bluetooth 5.1, but this is a very new technology that even the biggest firms in the world are in the R&D stage of. This rendered the usage of Bluetooth 5.1 technology infeasible to develop in the time we had. Secondly, we plan to use 4 ultrasonic receivers on the corners of the board as the writing device would have a transmitter that would transmit ultrasound, and we would triangulate the position of the writing device on the board. Due to lab closures because of COVID-19, we were unable to completely develop this solution. The last choice, and the one we successfully implemented, was using a high density of very tiny QR codes on a transparent sheet that would be placed on top of the board. A USB camera on the writing device would detect these, and decoding them would give the coordinates of where on the board is our writing device. So this is basically our system design. Here we can see we have two major sensory inputs. First, we have the optical sensor, which gets the fine strokes of the professor. The second is the USB camera, which detects the high-density tiny QR codes on the board. Once we have sensory inputs of both, we process them and we combine them using a Raspberry Pi. And then we convert them into digitized notes that is then thrown onto a virtual canvas that we created. This virtual canvas can be encompassed within a desktop application or a mobile application. So this slide presents the software flowchart. Over here, we were using 2 threads since we had 2 tasks demanding concurrency. One thread was getting relative movement data from optical sensor via Bluetooth. The relative movement data is sent in the form of series of arrays. Each array contains X coordinate move, Y coordinate move, clear board option, change board option in a multi-board setting, and some metadata. The other thread was detecting and decoding QR code data coming in from the USB camera. We use Raspberry Pi for processing, which used the data from 2 threads to output digitized notes on a virtual canvas. So this slide shows the main achievements and technical specifications of the product. This includes the small size, that is 2" by 3" of the clip-on device, 1,000 dots per inch optical sensor, so that small movements are also captured, sub-second QR read time, a Raspberry Pi 4 with 4 gigabytes RAM and a quad-core processor for fast processing. This enables presenting digitized notes on virtual canvas without any lags. So in this slide, on the left graph shows QR code read times. We can see that we were able to read consecutive QR codes in approximately 0.3 seconds as opposed to 3 seconds taken by commercially available QR code reader. We were able to achieve this because of various optimizations in our code, like capturing the smallest image possible that would contain at least one QR code, since we knew the density of QR code on the board. Smaller image size meant super fast detection of QR code and its decoding. The graph on the right shows the minimum readable size of QR code. We wanted to be able to read very tiny QR codes since we don't want chunks of QR code visible on the board. As we can see, the commercially available QR code reader read a minimum of 2 centimeter by 2 centimeter, whereas our solution detected QR code as small as 5 millimeter by 5 millimeter. This was primarily achieved because we had a variable focal length camera that could get super focused image from really close and post processing like magnifying the image before decoding. Now Theo will talk more about the budget.
So when it comes to the budget, our main goal was to achieve a device that costs less than $150 compared to other devices which cost much higher. So as you can see, our USB camera costs $80, our optical sensor costs $5, and our Raspberry Pi costs $40, amounting to $125. And if adding miscellaneous costs, this will cost $150 per se. Therefore, this achieved our cost. The next thing we had to do is how will our product impact the environment and other factors. Environmentally, we save paper from notebooks, and we save from the disposable expo markers that we save the environment. On the business side, we see that there's interest for our device and enables teachers and professors to distribute their notes easily. But the thing is, we had an ethical concern, and this involved this promoting absences from class and illegal distribution of notes. However, this can easily be circumvented if professors follow guidelines and create security patches and security systems around their notes. When it goes to the ethical standards that we followed, we used commercially available material that already implemented this standard. Thus, we didn't have to circumvent many things to follow such standards. This is the end of our presentation.
Awesome. So now the judges can go ahead and go on the desk post side and watch that first video. We'll see the demo. And then when everybody's done watching, if you can react with a thumbs up or type in the chat that you're done, that'd be great.